Okay, thank you. Thanks to the organizers for putting all this together. I know it's not so easy, and appreciate it. The work I'm going to be telling you about is joint with Grant Barkley. Okay, so I'll start by telling you what the combinatorial invariance conjecture and what these Kazhdan-Lusztig polynomials that appear in it are. So first, just a brief overview. So the Kazhdan-Lusztig polynomials, these are polynomials PUV in a single variable Q. U and V are permutations in the symmetric group. And these polynomials were introduced by Kazhdan-Lusztig because they have sort of an amazing variety of connections to lots of not obviously related areas of representation theory and geometry. So to singularities of Schubert varieties, to representations of GLN, and in terms of defining a certain special basis of the Heck algebra. This is the same Heck algebra that appeared in Sarah's talk earlier. So these are fundamental objects in geometric representation theory, but they're polynomials, they're indexed by pairs of permutations, so we ought to be able to understand them to some degree in terms of the combinatorics of permutations. So the relevant combinatorics is going to have to do with Bruja order. So this is a partial order on the set of all permutations of n. So on the left here, we have the partial order for S3. We can see that the permutations are graded by the number of inversions they have. So for example, 2, 3, 1 has 2 inversions, the 2 before the 1 and the 3 before the 1, so which is why it's at height 2. In general, the cover relations in this poset are given by swapping 2 numbers in the permutation in such a way that the length increases by exactly 1. You can see on the right here already for S4, this poset gets quite complicated, and it's really a very intricate and not so easy to understand poset. All right, so what are these polynomials? You don't need to try to process everything that's written on the slide. I will point out a few key features. So this is a recursive definition of these polynomials. So the first important property is that the polynomial is 0 unless u is less than v in Bruja order. So really, we're just going to restrict to the case where u is less than v in Bruja order and try to understand the polynomial PUV in terms of the interval between u and v in Bruja order as a poset. Okay, so there's this recursive definition. It defines the p's in terms of these other polynomials, these r's that are showing up in the last formula. I'll tell you what those are in a second. And I also want to point out there are signs in this formula. So it's not at all clear from this formula that the p's have non-negative coefficients, although that is in fact a very deep theorem. All right, here are the r polynomials that were showing up in the previous slide. They're also defined by a recurrence. So they're also 0 unless u is less than v in Bruja order. If S is a descent of both u and v, then we can undo that descent in both u and v and get an equal r polynomial. And kind of the most interesting case is this fourth one here, where S is a descent of v and not of u, in which case we recursively express the r polynomial in terms of smaller r polynomials. So the goal of this is going to be to understand these polynomials just in terms of the interval between u and v in Bruja order as an abstract partially ordered set. That is, without remembering the labels of the vertices, without remembering which permutation lives where. So a couple features of this recursive definition that make it not at all clear whether we're going to be able to do that are that, one, so this recursion depends on knowing about descents of u and v, whereas Bruja order was defined just in terms of swapping arbitrary, not necessarily consecutive pairs. So in fact, you cannot tell just looking at Bruja order which edges correspond to descents. The other thing I want to point out is that this case 3 here, when S is a descent of both u and v, that expresses the r polynomial for some pair in terms of a translated pair. And so in order to compute that, you leave the interval from u to v and you look at some other interval in Bruhat order. Okay, so with that in mind, what is the conjecture? The conjecture was made independently by Lustig and by Dyer at various points in the 80s. So the conjecture is that if two intervals in Bruhat order, so here U to V, this means a closed interval in Bruhat order. If two of those are isomorphic just as abstract partially ordered sets, forgetting the reflections that the edges correspond to, forgetting the permutations labeling the vertices, just two isomorphic posets, then the polynomials should be the same. And this is very surprising for, well, the reasons I pointed out, that the recurrence doesn't seem at all like it should respect this property. And also, these polynomials seem to encode so much deep geometric and representation theoretic information that it's surprising that just this pure combinatorics might tell us everything about them. So this has been proven in various cases. Sort of the most substantial of these is the second bullet point here. So various groups of authors around the same time in the aughts prove that the conjecture is true if both U and U prime are the identity. So if we have two lower intervals in Bruhat order and they're isomorphic, then the polynomials are the same. Okay, so here's some examples. So whenever the interval just has two elements, one less than another, the polynomial is supposed to be 1. Whenever the polynomial looks like this cube, or in general a Boolean lattice, the polynomial is also 1. Sort of the smallest intervals for which the polynomial is not just 1 are these 4 crowns. This happens in S4, for example. In this case, the polynomial is 1 plus q. Okay, so now I'm going to tell you about hypercube decompositions, which is a new conjectural approach to try to prove the combinatorial invariance conjecture that emerged a few years ago. And if there are questions in the chat, I hope somebody will interrupt me. Okay, so these hypercube decompositions were discovered in a rather interesting way. So there's this work of these 5 authors from, I think, 2021. So of these, Jordy Williamson is a representation theorist who's done a lot of work on Kazhdan-Lusztig polynomials. The other 4 work at DeepMind, which is Google's machine learning lab. And what they did is, assuming the conjecture is true, we're supposed to be able to take this graph, this Hasse diagram of a poset, and just from that information, produce a polynomial. So what they did is they trained a neural network to, given a graph, try to guess this polynomial. After they had done that, and they had a neural net which was good at guessing the polynomials, they somehow asked it which substructures of the poset affected its answer a lot. And after consulting their neural net for long enough, they figured out this concept I'm going to tell you about of a hypercube decomposition. So this is a certain substructure within an interval in Bruhat order, which conjecturally is going to allow us to write a Kazhdan-Lusztig polynomial as a combination of smaller Kazhdan-Lusztig polynomials, and therefore would imply the combinatorial invariance conjecture. All right, so what are these hypercube decompositions? First, I need to tell you about the Bruhat graph. So I'm going to write gamma UV for that. This is the directed graph whose vertices are the elements of the Bruhat interval from U to V. And we have directed edges whenever we have any transposition increasing the length, even those where the length increases by more than 1. All right, so here's the definition, and we'll spend a few slides unpacking this. So hypercube decomposition is going to be a special lower subinterval of our interval. So our interval that we're interested in is interval from U to V. We're going to look at the interval from U to Z inside of that. And this is going to be hypercube decomposition if it satisfies a couple properties. So the first property is that this set U to V has to be what's called diamond closed in V. And I'll give an example of that in the next slide. Then the kind of most important condition is the second one. This says that if we look at an element x, which is in our subinterval, and we look at the set y of x, which is all of the arrows leaving I based at x in the Bruhat graph, and if we look at a collection of those whose tops are incomparable in Bruhat order, then we're going to require these edges to span a unique hypercube subgraph of the Bruhat graph. Okay, and I'll give some pictures. Okay. So first of all, Bruhat graph, as on the left, this was what the Bruhat order looked like on S3, for example. As you can see, once we go to the Bruhat graph, we have edges for all the cover relations, but we also potentially have these longer edges, like the edge from U to V in this case. Okay, so what was this diamond closed condition? So here I've drawn the elements of I, these 4 vertices in blue. This collection is not diamond closed. So what it means to be diamond closed is if you have 3 vertices of some diamond subgraph of the Bruhat graph, then you must have the 4th. So indeed, this set does contain this diamond, but its bottom 3 vertices also form a diamond with this other element of height 2. And that the top of that diamond is not an I. Therefore, this set is not diamond closed. Okay, what about this set? So now blue vertex means I. The singleton, just taking z equals u, that is indeed diamond closed because it doesn't contain 3 elements of any diamond. So it's good from that perspective, but now let's check the hypercube condition. So what we're supposed to do is we're supposed to look at every element of I, so every blue element. Here there's just one. We're supposed to look at any collection of arrows leaving I from our chosen base element, such that the tops of those arrows are incomparable in Bruhat order. So for example, these 2 red arrows are such an anti-chain. Now the hypercube condition says that those 2 edges are supposed to be the bottom edges of a unique, well, 2 hypercube. A 2 hypercube is just a diamond. So these 2 red arrows are supposed to be the bottom of a unique diamond, but again, we see that's not the case because there are 2 ways to complete these 2 to a diamond. Both of the elements of height 2 work. Okay, so this satisfies the first condition. It is diamond closed, but we don't have the hypercube condition. All right, here's a further non-example. Again, taking u equals z, that's diamond closed, but consider the 3 red edges. Those are an anti-chain. Whereas before, the problem was that we had the red edges spanning more than 1 hypercube. Here, they don't span any hypercube. There's no 3 cube sitting inside this graph with those 3 red edges as its bottom edges. So this fails the existence rather than the uniqueness of the hypercube condition. All right. Finally, I will show you a positive example. If we take the 2 blue elements as I, that's diamond closed because I don't have 3 elements of any diamond, so I don't have to worry about it. And we can verify the hypercube condition. For example, we can verify it at x equals z. So here there's only 2 arrows leaving z, and indeed there is a unique way to complete them to a diamond. So this does form a hypercube decomposition of this Bruhat. Okay, so again, there is their definition. They proved this theorem here that there's a specific choice of z called the standard hypercube decomposition, which gives a hypercube decomposition for any interval. So the important fact there is that every interval does indeed have some hypercube decomposition. One fact about the standard hypercube decomposition, though, is that we can't tell just from the underlying graph or just from the underlying post set, which hypercube decomposition is standard. So that's we need the permutations for that. Okay. So I think I deleted this slide, but what these authors did is they then made a conjecture that whenever you have a hypercube decomposition, you have a certain expression of PUV in terms of PUVs for smaller subintervals using the structure of the hypercube decomposition. One of the reasons I didn't include their conjecture is because it's very complicated and I think overly so. And so what Grant and I do in our work is we reinterpret hypercube decompositions, not in terms of these P polynomials, but in terms of the R polynomials. And in this setting, there are simpler conjectures that one can make about hypercube decompositions. And we've been able to make some progress on proving those conjectures. Okay, so I need to actually tell you about a slightly transformed version, the R tilde polynomials, of these R polynomials that we saw at the beginning. So this R polynomial on the right-hand side here, this was the thing that appeared in the recurrence for the P's, which had a recurrence in terms of descents. We're going to look at a slight transformation of this. So these R tildes satisfy this variable transformation with respect to the others. Now, because you can combinatorially go from R tilde polynomials to R polynomials, and with R polynomials, you can recursively and in a post-set theoretic way build up the P polynomials, it's in fact equivalent to prove combinatorial invariance for the R tilde polynomials rather than the P's. So our new goal is to try, given isomorphic intervals in Bruhat order, to prove that the two R tilde polynomials are the same. The advantage of these R tilde polynomials is they have a somewhat more combinatorial formula. It still won't be good enough. It still won't be just in terms of the post set, but it's at least a place to get started. So a reflection order, this is a total order on the set of transpositions in Sn, such that if A is less than B, less than C, then the transposition AC has to lie between the transposition AB and BC. What Dyer proved is that if we've fixed our favorite reflection order, then the coefficient of q to the k in this R tilde polynomial is the number of increasing paths in the Bruhat graph from u to v of length k. And by increasing, I just mean that each edge in our Bruhat graph corresponds to some transposition. We require that the sequence of transpositions we see along our path is increasing with respect to our fixed total order on transpositions. So it's not at all obvious from what I've told you that this count should be independent of the reflection order we've chosen, but in fact it is. So the reason this doesn't solve combinatorial invariance is that it requires knowing which transpositions label the edges of the Bruhat graph, which is not something we're allowed. We're only given the plain old underlying graph, no labels. But still, it seems that hypercube decompositions allow us to write some recurrences for these R tildes. So first, let me give you an example of how the R tildes work. So in S3, we've chosen the reflection order on top. This is the Bruhat graph. If we look at increasing paths, there's this one increasing path of length 3 and one increasing path of length 1. So the R tilde polynomial is q cubed plus q. Okay, so here's our definition. So we take a hypercube decomposition of uv. So we have the same objects as them, but working with different polynomials. And we define this polynomial h tilde here. Okay. So this is a sum over the elements of I, so a sum over the elements of the subinterval. Then for each element there, this theta is the top of the hypercube that this antichain A spans. So what we're doing is we're summing over those elements such that they have a hypercube which does in fact reach V, then the width of the hypercube, q to the width of the hypercube, and the smaller r tilde polynomial from u up to the base point of our hypercube. So this is a definition. Our conjecture is that for any hypercube decomposition with an additional technical assumption, which doesn't affect too much, the strongness here. If we have any such thing, then coefficient-wise, we conjecture that h tilde is at least as big as r tilde. Furthermore, we prove that for the standard hypercube decomposition, you have h tilde equals r tilde. So, in fact, this conjecture does imply the combinatorial invariance conjecture, because if you give me a poset and don't tell me any labels, I can find all the hypercube decompositions. I can recursively compute all of these h tilde polynomials, and then I can take the coefficient-wise min of those, and that will have to be the polynomial we're after. So this would indeed resolve the conjecture. The strongness that we had to add compared to the Williamson et al. Definition, I'm going to skip over. It's a technical condition that's not so important. It's still the case that the standard hypercube decomposition satisfies this, so we always still have hypercube decompositions, and it's still defined only in terms of the underlying graph without labels. So it's completely fine for us to impose this additional condition. And in fact, we're not sure if there are any hypercube decompositions which don't have our property, but we didn't work too hard on that. Okay, so here's an example of how our formula would arrive at the polynomial we computed before. So our polynomial says to sum over the elements of I, to sum over the two blue elements. For each of them, we're looking at hypercubes leaving that element which reach the top. So for U itself, there's one such thing, which is this one hypercube, which is the green edge itself. So that's going to contribute this q to the 1 times RUU. For Z, we have this with 2 hypercube, the red one. So that's a q squared times RUZ. Assuming we already know our polynomials for smaller intervals, we know that this is q times 1 plus q squared times q, so we get the same thing we had computed before. All right, what's the theorem? So let me define a class of intervals. So whenever we have an interval, let's look at the cover relations above u. So the things just above u in the order. Those correspond to applying some transpositions to u. Let me call those transpositions, these I1, J1, I2, J2, and so on. Transform each of those into a vector. So instead of swapping, I and j, look at the vector ei minus ej. If that collection of vectors is linearly independent, then we say our interval is simple. If they're not necessarily linearly independent, but our interval is isomorphic to some interval in which they are, then we call the interval elementary. So the theorem is that if we have any elementary interval, then in fact R equals H. And therefore, for those intervals, we can prove combinatorial invariance of these R tilde polynomials. And I'll point out that this, even the simple case, the case of simple intervals, is a significant generalization of the case of lower intervals. Remember, the case U and U prime being the identity was the biggest known class that for which the conjecture was already known. In that case, the cover relations of U are just simple transpositions. So they look like I swapping with I plus 1. Any such collection of those vectors, ei minus ei plus 1, is linearly independent. So in particular, lower intervals are simple, but the simple intervals are much richer, and the elementary intervals richer than that. That's all I have. Thank you.
Okay, thank you, Christian. So to start out questions, I think there was a question in the chat from a little earlier. So Jake Levinson asked, does the set of all reflection orders have any structure?
Yes, it is in it's in bijection with reduced words for the longest element. You can think of it if you write a reduced word for W naught, and then you multiply it out step by step. At each step, you will gain one new inversion. And if you look at that ordering of inversions that you get, that's exactly those are exactly the reflection orders. But in the case of infinite groups, for which Dyer's theorem still works, then they're kind of their own thing, because there's no W naught.
That's cool. Other questions?
Hi, Christian. That was a really nice talk. So how much of this is particular to symmetric groups compared to sort of all Coxeter groups? Because I mean, a lot
Right.
of it for,
so the conjecture applies to arbitrary Coxeter groups. The hypercube decompositions are currently only for the symmetric group. So it's not true that intervals in general Coxeter groups always have hypercube decompositions, and it's not known what is the correct generalization of them. Yeah, good question.
So how come they're not running DeepMind on type B or something? We need a...
Well, I don't. So I think what they actually got from the neural net was a bit inconcrete, and a lot of the definition of hypercube decomposition was really because Jordy Williamson knows a lot of stuff and was able to figure it out. So probably the right thing to do is instead just think hard about hypercube decompositions and think what the right analog in other types is.
Thanks.
Human intelligence rather than artificial intelligence, I think.
Cool. We have time for one more question if there's any other questions.
I mean, I have a question. So, I mean, it seems like in some cases you do have these decompositions, and so you can define your H tilde polynomials for like things that didn't come from Bruja order. And does that I mean, does that seem like a thing?
So you're asking, when my interval in another type happens to have a hypercube decomposition, does the formula hold?
Yeah, I mean, I guess, I mean, you have a definition basically, right, at that point?
Right. Well, for any interval in another type which happens to be isomorphic to one in the symmetric group, then because combinatorial invariance seems to be true, the formula seems to hold. But I don't, yeah, I mean, it's a good question. I don't know anything very concrete about other types.
I mean, in theory, it wouldn't even have to be from a Coxeter group. You could just have the poset structure.
Yeah. What are you computing? I wonder. Yeah. Yeah, it's interesting. It would be cool to look at hypercube decompositions of your favorite posets, maybe, but it does feel quite attuned to Bruja order, so I would guess you'd want some, Eulerian thing with, like intervals or diamonds, or, like at least save some of the properties of Bruja order like that.
Okay. Any other questions?
Okay, can I just ask a quick silly question, maybe sort of in this direction? Is there any, can you like sort of move any of like these hypercube decomposition things to like the matrixal version of Kazhdan-Lusztig polynomials?
I haven't thought about that. I have wanted to think about Kazhdan-Lusztig polynomials of matroids. The problem is that I don't know what the right question is, because they are they're manifestly combinatorially invariant. The definition is combinatorial in this sense, and so
yeah, I guess the question would really be like, does this mean anything reasonable for matroids? But I don't know. Yeah, I guess yes, they're inherently combinatorial. So I guess the original question itself doesn't quite make sense, but
right. it would be interesting to see if some of the same formulas had analogs, but the conjecture itself, not, yeah. it's not-
Right. Yeah, I guess the question then would be like, is this something sensible? Has something having to do with matroids or geometry related to it? But yeah, I guess it's unclear.